you get a non-negative number. So the absolute value is primitive recursive. So primitive recursive function produces many things, and so far so good, but I wanted to kind of change one thing here, and that is, let me just put here, this will be example, because I can't count. That's example 7, example 8, and this is example 9. So that's 9 examples of primitive recursive functions. So let's go back here and put 7. Example 7. Example 8. And example 9. Okay, good. Now, what was I saying? I was saying, so let me save that. Save. So I don't lose it. Okay, save. Yeah. Okay. So the primitive recursive functions, you know, things like example 5, example 6, example 7, example, oh sure, so I have 2 example 7, no, example 6, example 7, that's page 7. Example 8, example 9, and these are all, you know, reasonably nice functions. The problem comes up when we are asked to find things like this. Bonsoir, right? Thank you, Ms. Rashi. Sometimes I know things without knowing it, right? So where are we? We are at this thing F2. So we forget F2, F1, right? So all of these guys here have this, you know, ceiling function thing, and it makes it awkward because you're thinking, you know, I don't like this. This makes it like not what you would call smooth, you know, addition or multiplication, even subtraction. They're like relatively smooth things. But something with like, okay, get the fraction and then cut off a piece and then throw away the fraction and keep the integer, that looks a little ugly, right? So, and this one is called ceiling. So you round up, and then you're thinking, can you round down? And it turns out rounding down is difficult in recursive function. So why? Because that's how life is, you know. I mean, it's like we can make people taller, but we can't make them shorter, right? So let me put in Nguyen Hansen. Nguyen, welcome to the class. Okay, good. So save. Okay. Now, we did the last time x over 2, and I told you the secret there was you put x over 2 is equal to y. So let me just kind of write that here. You say something like, hey, x over 2 minus y is, you know, that is my g, right? But then you say, hey, that's a fraction and so on. And you say, okay, round it up so it doesn't become a fraction, and then do your magic and do the minimization on that. X minus 2y. So you say, oh, that's how you got that. Correct. And then you say, this one here, you do the same thing, 2x over 3, right? So I'm showing you all the tricks of the trade here. And then you subtract this y or whatever, you know. And then you say, hey, you know, I should multiply both sides by 3 because I don't want any fractions or whatever I do, just want integers. And that's how you come up with this. Now, that's showing you how you come up with it, but you still got to check everything works out, right? So, but so the question I always get from the student is, how did you come up with this 2x over 3, 2x minus 3y? So I'm showing you here, and this is like what gives you that. And you're thinking, oh, okay, from this you get that, and from this you got this, right? And then the key point is that this thing works and that this thing works, but this wouldn't work because this is a fraction, and you don't have fractions in natural numbers. Then this one here, you do the same thing. You're like square root of x, you know, minus y, And then you're thinking, okay, so you can't multiply anything but that. Then you say, okay, square root of x is, supposed to be less than or equal to y. And then you say square both sides. Then you say x is less than or equal to y squared. And then you say, okay. And then from that, this becomes a little more problematic. And then you get x minus y squared. X minus y squared. And you're thinking, okay, I think I can do that. That's how you get these. So you're thinking, okay, I got the tricks of the trade, That looks ugly. So I am going to put it like so. And put x minus y squared. And you're thinking, okay, that should do the job. Okay, so we got that. Now, when it comes to the next guy, right, x over 2, right, these functions here were all defined, because if you take any number and you take the square root, you can round it up, you'll always get an output. But when you take something like, you say, I wanted to get x over 2 if x is even, and I want it to be undefined, that's saying that it doesn't produce a number, then that's a little problem, right? So this one, we all know the trick. It's like the smallest y such that x minus y is equal to 0. So that really means x is less than or equal to y, or x minus y squared is equal to 0. So you're thinking, okay, I got this. So this is good. This one is a little harder. And while I'm letting you think about it, let me put in before I forgot, Jonathan Barletier. And that's it. Nobody else is here. If you are, tell me, give me a little shout, saying Professor number 33 is here. Okay. So, what do we do here? Well, the idea here is you say, I want something that will make this 0, x upon 2 minus y will go to be 0. And then the y minus x upon 2 is going to be 0. So you want, remember, so you want x over 2 minus the y, that to be equal to 0. And so, and then you want to say, hey, I also want y minus x over 2 to be equal to 0. All of that. And so let me take out this thing. It looks very bad here. Y minus. And that you want to be 0. So you're thinking, oh my God, let me put, instead of, this is bad. So apologize for that. I should put, not absolute value, because that means something else. ABS, I should put the wrong bracket. So you want this to be, because that cannot be negative, and this cannot be negative. You want both. And you're thinking, okay, you want this to be 0, and this to be 0. And if it's not 0, then this will be undefined, because what is the mu operation? The mu recursive function means you're looking for the smallest y in which this condition is satisfied. And if there is no y, and then, of course, this is not what you want. You want this. So this is what leads you to this. Now, why is this unacceptable? Because you're talking about x over 2, and that is not defined. So everything has to be defined. So here, everything is defined. And then you're thinking, okay, I wanted to get this. So you said, okay, I will look for the smallest y so that g of x comma y is equal to 0. That's the standard thing, the minimization operator. You think, okay. Let me get a little drink here. Because after one class, my throat gets dry. Santa Maria de la Caridad. Okay. ¿Qué pasó? I gotta take this out. I don't like you. I gotta make you nice. So this is, okay, that's that. Now, G is a total function, and when you do this thing, you get the smallest value of y such that this thing turns out to be the absolute value of x minus y. So you are thinking, Professor, what happened to the dot? Well, remember, the dot means monos. The dot does not give negative number. But when you have the absolute value sign, that gives you positive and negative numbers. But then you take the absolute value, you get positive integers or non-negative integers. So you're thinking, okay. So ABS, I call it ABS. So this thing here is ABS of x comma 2y is the difference between x and 2y. how far it is. And then I realized that, oh wait, this guy works, if y, if x is even, then there is a unique y, the x upon 2. And that's what the smallest y will be, is the only y, right? And then, but if x is not even, no matter what, you do till thy kingdom come, you could work, you will never get any value. And when x is odd, this thing is greater than equal to 1, so let me underline that. And so this thing now produces, right? It's not only sort of round up, it produces the exact value of the thing if it's an integer, and if it's not an even, if it's not an integer, if the answer is not an integer, it says undefined. If it becomes like 3 upon 2, it's like, okay, 3 upon 2 is not an integer, so undefined. But 4 upon 2, 6 upon 2, 12 upon 2, all of these are defined, so these will give you the answers. 12, you put x equals 12, you'll get 6. Okay, I think I got that. Good. Now, here's another thing. Now, of course, before I rush, I want to emphasize, what do? You got to do two things. So I told you the secret of how to get this, the G. That's one thing, right? And then the only other part you have to do is you have to say, massage the G and say mu G comma 0, and then you got to make the G into a primitive recursive function. And it depends. If I tell you you are allowed ABS, then this is the answer, you're done. If I don't tell you you're allowed, you have to put it, right? So if you have to put ABS is equal to this, you put where the ABS is, you put this whole thing and you put it there. And the whole answer can still fit in a line, right? But it depends on what you're told. So if in the question it says you may use spread, add, mult, monos, those are always given, and ab, ABS, then you use it, and then you're done here, right? And so this is what this problem is done. Now let's look at another problem that is slightly different, and this time it is f5 of x equals x to the 1/3 if x is a perfect cube, and undefined if x is not a perfect cube. So things like 8 and 27, you will get the answer for 8 is 2. Answer for 27 to the 1/3 is 3. 64 to the 1/3 is 4. But anything else, you will say undefined, because you get fractional numbers, right? And so you think, okay. So when you look at a thing, you're thinking, hey, I'm using that same trick that you used there, right? I will take x minus y cubed, and then he said, this is that, and which is the same thing as like this. So it depends if you're allowed. If you're allowed ABS, you're good. If you're not allowed ABS, you will be allowed monas, so you can do it like this. But it just depends on which one you're allowed. And, as I said, when I get questions, sometimes they allow, I get accreditation questions. Sometimes they allow ABS, sometimes they don't allow. And last semester, they didn't give me anything, but I only know on the last week of class whether I get embedded questions. So keep that in mind. So you got to know whether to use ABS or not, right? And as I said, err on the side of caution. It doesn't kill you to know what ABS means. So you can just put, instead of ABS, you put this, x minus 2y plus 2y minus x. That's what the absolute value is. So it's not hard. All right. But let g of x comma y equal this, which is abx of x comma y. And if you want it in longhand, it's x. This is equal to x minus y cubed plus y cubed minus x. And the dot is not showing good, so I gotta put a little bigger dot. Y cubed minus x. And let me make this here, a seeable dot. Good. All right, so you could just put that. But I am putting variations to make you see everything. Then you say, then it is not difficult to see that this. And so this thing here works because x to the 1/2, I put y squared, x to the 1/3, I put y cubed. You think, okay. And then I got to write this. Now, here is the part that sometimes students get wrong. So you're thinking, okay, I know you have abs, that's this. and you want x, so that's I12 because the G is got two variables, x, so that's how you get the I12. I'm showing you the tricks of the trade. And the Y is your second input, and I want y cubed. So you say, okay, multiply second input by second input, all of this produce y squared. And then multiply by y again, right? All of this produce y cubed. You're thinking, oh, okay, I see how you get a y cube. And then you get the difference between x, so this is your x here, and your y cube. And you're thinking, okay, x minus y cube absolute value. And that's what the absolute value is for, ABS. And you're thinking, okay, you got it. And then you say F5 is recursive. Now, we are going to do some tricky things in the next few questions, but then we will be finished with all of these things. And as I said, none of this is hard. It's just that it is strange. That's the only word I will use. And I want to make this thing here a little nice because it's not pretty. I want to make it a nice curve. You know? Okay. So what is my point? It is not hard because you just have to remember what things are and how to kind of always exploit what is the input and write the output in terms of the input. You want x minus y cube, right? You don't have that minus sign. You have to take this. That's why I didn't like to put this. But the textbook does it, so I do it, right? So x minus y cube, you say, okay, x minus, I got that, plus y minus y cube minus x. And then so you got to write this in terms of this. And you're thinking, how am I going to get y cube? Okay, I can get x easily. That's x. And y cube, you do 2 multiplication. You're thinking, oh, okay. And this is the part that students get wrong because they like to say mult of mult of mult. But no, you can't say mult of mult of mult. You got to say what is the input. So that's why I said this is a y and this is another y. When you do the mult, you get y squared. But if you just put mult, that's mult is going to take the 2 input and give you x times y. And then the whole thing is going to be wrong. And then the student is going to say, oh, well, professor, you put the same thing. No, I don't put mult. I pick out the thing I want, the y, and then I put mult of y, comma y. And then you're thinking, oh, okay, I see. All right, so I fuss about this because every year I teach the course, and every year students hate it. And I'm thinking, okay, you can hate the course, you can hate the textbook, but, please don't hate me. But, some still end up hating me. But I teach it because that's my job, and it's not fun. But anyway, leave that aside. I want to take this off here. And I want to kind of put a double line like how I put a double line around it. Why? Like that. And I want to go to this function h1. So what is this function? h1 is telling you is like modular arithmetic. So you're thinking, oh, yeah. h1 is 0 if you're even and 1 if you're odd. That's modular arithmetic, modulo 2. Right. And so let me put this y cube here because it is interfering. I hate it here. So I will put a y here. And I'll put the y cube here. When you multiply everything, you get a y cube. Right? Okay. So you're thinking, oh, this thing can do modular arithmetic here. So h1 is the modular arithmetic. Show that f is recursive. So I made a mistake here. I should say show that Santa Maria. There is no f. What are you doing? The guy name is H1, so man, I don't know. I hate that thing. So show that H1 is mu recursive. Okay. So then I say okay. How can I get h1 in terms of the functions that we know? So you're thinking, you know what? If I multiply x over 2 by 2, and then I subtract x, I will get 0 if x over 2 was an integer. But if this was like, when you round up, you'll get a little more, and then you'll get 1. And you're thinking, wait, let me see. Suppose x was 7. So you say 2 times I need red because this is adding. Say red. So you say, okay, let's try 2 times 7 over 2. Right? And then you subtract the 7. So you're thinking, okay, that is 7 over 2, 2 into 4. Right? Or if you like, you could put a dot. So 2.4 minus 7, which is 1. And you're thinking, yeah, for any odd number, you'll get 1. So this confirms that just for 7. But in any odd number, you get it. Then you say something like 10. 2 times 10 over 2, 2 5 10, minus 10, 0. So you're thinking, yeah, this works. So this is the secret. Right? And I don't know why I put F1. Okay, now I know why I put F1. F1 is that, F1 is that first function, the x over 2. F2, that's F1, right? So I did the dirty work there. So where are we? Here. So you said, okay, I know what that is. So this guy is monos of 2F1, and then there is a little extra dot there. I don't know where he came from. Right? Okay, 2 times f of 1 of x, comma x. And you're thinking, okay, I think I know, because this guy here is the f1, and that's the 2, and then you monos the x. And where f1 is that. Now, then h1 is monos, and then you need to get 2. So how are you going to get 2? Again, this is another important point. All of this is just 2. You're thinking, you got to do all that stupid thing just to get 2. Yes. So this is the second input, right? F1. The first input is 2. You're thinking, okay, I am not sure what is going on, but your H1 has 1 input. So you pick out that 1 input, the x. So this is basically I1, 1 of x. Then you take the z, you make it 0, then you take 2 sections, so you get 2. So, you get 2 here. But this 2 has got the same, level of complexity of the F1. You are getting an x as your input. You're thinking, okay. So you produce the 2, and then you say multiply that 2 by the F1 to get 2F1. And then you want to subtract the x. So using monos of all of this, and then you subtract an x. So you're thinking, okay, so all of this were together, and then this is by itself I11, which is the x, and then you say this minus x, and you say, okay, monos, not minus, monos. And you're thinking, okay, and then I see H1 is made up of the primitive, the initial functions from these things called monos and mol. And if necessary, and now I don't tell you to do this, this is why in number 4 in the exam, I say, take the whole chunk of mult and just chuck it in there. Take the whole chunk for monos and chuck the whole program there. But you don't have to, because that's waste of time. If I give you permission, you just put monos. And you say, okay, he gave us permission to use monos, so we're going to use it as a built-in, procedure or built-in function. So you're like, okay, that's good enough. And look, I did that because I want the answer to be 1 line. You're thinking, okay, if you say so, but if you're playing with a machine, then of course, all of these are nice, but that you have to write the whole program. And this you have to write the whole program. But this is 1 line, and this is half a line, and this is 1 line. Because this involves addition. So this is a whole full line, and this is half a line, but the whole program takes no more than 2 lines. You're thinking, okay, but as I said, I don't want to waste your time. I want you to see the big picture. The big picture is you just write this and you say you're done, right? And this is recursive, so you put the program for that. This is recursive, and this is recursive, and you get H1 is obtained from the initial function using all of this. And you're thinking, but professor, where is the mu recursion coming in? It's coming in the F. So let's look back what F1 is. F1 is got mu, see, mu, monos, whatever, that's the whole F1. It's a line, or 3/4 of a line. So the F1 has the mu, and so that's where you get your mu from. So far so good. I think I need to take a Halls or whatever to make my throat not get sore. I probably should avoid back-to-back classes too. Hey, come on. Okay. Hopefully this will help. All right, so I got that, I got this, and now I am get another guy, H2. So this H2 is a little different. This one was basically, if x is even, you put 0. If x is odd, you put 1. You're thinking that's modular arithmetic. Now, what is this other one? This one will produce 0 if x is a perfect square and 1 if x is not a perfect square. So you're thinking, oh, Professor, we did that. X minus y squared. No, what was that? X minus y squared, that produces this, F3. And that is not this, 0 or 1. You want to say the thing is a perfect square, and 0 means it's a perfect square, 1 means no. So sometimes some students are confused. They're thinking, Professor, why do you say 0 is yes and 1 is no? Well, you could do it the opposite way. But this is how the logicians do it. But it doesn't matter what you say, as long as you explain that 0 will mean yes. So 0, it says here, 0 means your perfect square, right? If you want, you could change it to 1. So all I got to do is to put 1 minus this. And so 1 minus 0 is 1, and 1 minus 1 is 0. So you can flip it anytime. But I just put it how the books put it. All the standard books put it like this. So you say, okay, I want to show this guy is a perfect square. And also I want to show A3, which is the opposite of this. I want to also show this is mu recursive. Now, I didn't have the word here mu, right? Because first when we did this and I wrote it, the textbook doesn't say mu recursive. I was following the textbook blind. And then I said, I should tell them that this is mu recursive because why? To distinguish it from primitive recursive, so because when you say recursive, everybody's going to ask, are you saying primitive recursive or mu recursive? Which one? And the idea is that if you don't say anything, it means mu recursive. But it's better to spell it out. So in the exam, I kind of spell it out, show that this is mu recursive. So if there's no doubt, you got to use the mu operator. And then you're like, okay, that's better. But the textbook doesn't say that. The textbook doesn't say mu recursive. It just says recursive, and I was following it. So what I do is I say, you know what? I am going to use that same trick here that I use for H1. When you take the 2 times 7 over 2, and you subtract, I get a minus there. I got to put that dot, right? I get 1. And make this minus dot bigger. Okay, so there I put 2 times this minus the x. So here, I'm going to put the round up the x square and you minus the x. Now, if the x is a nice number, a perfect square, and you take the square root of x and you square it, you'll get back x. And you're thinking, okay, that's x minus x, you get 0, and then you're saying, good, right? Sine of 0 is 0, right? And if it is not, when you round it up and you square it, you'll get something bigger than 0, but you won't get 1. But that's what the sign is all about. The sign will produce the 1. So you're thinking, oh, that's a nice trick. So we did it here in H1 because this produces exactly 1 and 0. It produces, 0 and the thing is even. And it produces 1 exactly when it's odd, like here. But here, it doesn't do it exactly how you like, right? What you do is you get something, and let's say, for example, you want square root of 2, right? And let's take something else, say square root of 3. So you take square root of 3 and you say, okay, round it up, you get 4. Sorry, no, let me write, that's the best thing. So you take square root of 2. Then you take the integer pi, the ceiling function of it. And then you square that. And then you subtract the 2, right? What do you get? Now, square root of 2 is 1.414, so this becomes equals to 2 squared minus 2. which is, why did I put 3 there? God knows what. 2 squared, minus 2. 2 squared. Minus 2, which is 2. And if I were to take square root of 3, take the integer part, let me take square root of 5, say, I don't like 3. Because I want a strange number. Square root of 5, not too big. What is square root of 5? Square root of 5 was 2 point something, because it's bigger than that. And then you square it, and then you minus the 5. Okay. Then you end up getting that is 3 squared minus 5, which is 4. So 9 minus 5, 4, yeah. And then you're saying, okay, I see what you're doing. So in order to get 0 and 1, that and that, you got to take the sign of this. So if it was square root of 4, and then you square it, and then you minus, 4, you will get exactly 0. So you're thinking, okay, that part is good. But I still want to say sign. Why? To make sure I get 1 when you are an odd number or a non-square number. You're thinking, okay, this is why I put the sign here. And then now I can say, therefore, H2 is equal to sine of monos of, then I multiply this guy, F3 and F3. Excuse me. F3 and F3. And you're thinking, what in the world is F3? F3 is that guy for square root, right? When you round up the square root, ceiling function. So F3 and F3, let me show you again here, F3, F5, F3 is the square root guy down. See? And now you say mult of this and this, that's this. And then this is the x, I11 of x. So you're thinking, but why do you put stupid thing like I11 of x? Right? I will explain. Okay, so I wanted x. And then I want to say, I wanted this minus this. And then I wanted the sign of it. So why do we put I11 of x? Because in the end, I can say, therefore, H2 is sine composed with monos, composed with mult, composed with F3 and F3, and second input for this, for the monos here, right? Because you are taking this and you are monosing this, is I11. So you are not allowed to have X in this thing. And that's why I put H2. So I have a program for H2. And you're thinking, Professor, I am tired of your crazy programs. Well, that's why people are tired of theory of algorithms. But as I said, there is nothing I can do. And it's shorter than any modern programming language. But, so the H2 is this. And then you're like, okay, it's not so bad. And then you said, this is the whole program for H2. Look how short it is. And then you said, therefore, this guy is a mu recursive function. So if you want, you could keep putting mu here, right? But as I said, when I wrote the notes, I was following the textbook and I didn't put mu. But now I am emphasizing mu. Now, the second one, H3, is basically 1 minus H2 of x. And you're thinking, okay, so I will just put H3 is equal to, so remember, this F3 and the F3, you got to put that whole program. F3 is here. F3 has a whole program, this whole thing there. You're thinking, man, okay, I will just take the whole thing and chuck it in. Yes, you take the whole thing and you chuck it in for F3. Where is that F3? Here and here. And then here, you chuck in the whole program for H2. So you put this whole thing here, and you just take monos is the monos. You want 1, you take this. And again, it's that ugly looking thing you're thinking, oh, Professor, why do we have to think about the input? Well, the input is x. So it's I11 of x. The I11 tells you, you pick out whatever you get. Then the z makes it 0, the s makes it 1, so you always get 1. And then the monos, this is the first input for the monos, and this is the second input, so this monos this, and then you're good. You're thinking, okay, I got a program for H3. Now, here is the last ugly one. We are looking at H4, which is floor function. So you're thinking, professor, I hate this floor function. I don't want to see it. No, but it's important because if you have ceiling, once you have ceiling, you need to know floor, right? So what is H4? And I deliberately change from F to H because G is usually a total function. When I put G, I want you to think total function and you're going to do minimization. H, I want you to think like, okay, it's like F, but I want to say it's a little different. So it's floor function of square root of X. So you're thinking largest integer less than or equal to square root of X. Yeah. And then you're thinking, man, I don't know what that is. Well, here is the idea. If the guy is a perfect square, right? So if somebody is so I can say, what is floor? Floor is the same as ceiling if you're an integer. But if you're not an integer, the floor is one less. So let's draw back that thing here again. So you have some crazy number, Z. That's not 2. And then you have the ceiling. That's Z ceiling. And that's Z floor. Like that. Okay, but that is if Z is not a natural number. So you can see, if you know this, you will know this, because this is that minus 1. But if this guy was sitting on here, the two of all three coincide. If Z was an integer, all three, ceiling, floor, and you're thinking, man, this is weird. You mean like 6, ceiling of 6 and floor of 6, and 6, they're all the same? Yes. 17, ceiling, floor, 17, because it's an integer. So if you're an integer, floor and ceiling and the Z are all equal, right? So maybe I could put here, it's also equal to Z if you like. And you're thinking, oh, but this is not equal to Z, this is different. So you're thinking, okay, I got it. But, it could be confusing. But in computer science, this is your bread and butter, ceiling and floor. So I want to get H4 in terms of H3 or H2 or whatever, right? So I'm thinking, I know it is this minus 0 and this minus 1. So you're thinking, right? Then you're thinking, oh, I have a thing for it. H4 is square root of X, floor function, ceiling function, this, minus the H2, which is the 0 and the 1. You're thinking, you're done. So this H4 is F3 minus H2. So I can write H4 now as a program. Minus composed with whatever the F3 was. And, this is an input, H2. And you're done. You're thinking, man, this is not so bad. Now, all the ugly programming is finished. So you're thinking, oh, praise the Lord, And I had a nice story to tell you about praise the Lord. But, I think that story has to wait, because I have talked about semi-recursive functions. Let me see, semi-recursive. Yeah, these things are going to take time. So I want to finish today's chapter today. So if you are curious, I will tell you about praise the Lord next time. But it's a very nice story. So suppose we have, what are we going to talk about here? Recursive and semi-recursive relations. Now, remember, we had the same thing. We had recursive, not recursive, Turing definable and Turing semi-definable. And it turns out these are all the same. So let me give you a preview so that you can see ahead how things are similar and how you can use ideas. Turns out, Turing computable is basically the same as recursive. Turing decidable is recursive relation. Turing semi-decidable is semi-recursive. Turing decidable language is recursive language. And then Turing semi-decidable is recursive, semi-recursive. And sometimes they call it recursively numerable. That's at the end point of all of it. But let's go back and work, with things. And maybe when I'm here, I should tell you this too. So you can get a big picture. Remember, we had finite languages. Now, finite languages are very boring because, why? They don't, the way to specify a finite language is to give you, write it out in longhand and tell you all the strings. And that's terrible if you have a finite language. Because if you have a million symbols like English language, suppose I said, can you tell me what are the, what is English language? The guy goes, okay, check Oxford English Dictionary because You can't take Webster because that's made in America. Oxford English Dictionary, that is the English language. Whatever words you see there, that's English. If it's not there, it's not English. Some people will disagree, but I'm just giving an example. So English language is terrible because it has a finite number of words, and there's no pattern. There's no pattern to the spelling either. But French and Spanish are a little bit better, and Italian. So the point is, finite languages are very boring and not interesting. But regular languages, they have a pattern. And the pattern can be obtained by, finding regular expression. And then it's equivalent to regular grammar. It's equivalent to finite, NFA or DFA, acceptable languages. And then you're thinking, okay, regular languages are nice. And you intersect two, you get regular, etc. You union, you complement, everything is regular. Then there's something called bilinear language, and we didn't study that, but those are not so nice. That's one of the reasons we didn't study. And then the syllabus is limited. Then there's context-free. Now, context-free is half nice. You can do all the union, intersection, concatenation, star, but you can't do complement or intersection. So you're thinking, okay. And then context-sensitive, we know very little about it. And then recursive, we know a lot because of Turing machine, etc. And then recursively enumerable is sort of like one step beyond recursive, which is a little bit complicated. And then after that, you have, things that are like, the best way to call them is like, impossible to talk about. Because if something is not recursively enumerable, what does recursively enumerable mean? In layman's terms, it means that you have a program that when you input one, it will generate the output. You input two, you'll generate so you can generate it, you can enumerate it, but you can't have a thing to say yes or no. Yes or no is recursive, that's decidable. But in the case with recursively enumerable, you could generate it. And so it's like, I'll give you an example in real life that is recursively enumerable. You take any axiomatic system and you say, I have proofs. I want my machine to prove. So they have things called machines that are proving things. So you say, okay, you let the machine look at all sequences of strings, formulas, and you say, is this a proof? And then if it is, you say, okay, I got a theorem. And so in that way, you can enumerate all the theorems, but not at one shot, not in a finite amount of time. And you can't tell me, is this a theorem or not? But you can enumerate the theorems, consecutively. So if something is a theorem, eventually it will show up because you're enumerating them, but you don't know when. But you don't have a method to say, okay, this is a theorem or this is not a theorem. Because if the guy is not a theorem, you can never know because you will never generate it. But you cannot know because you will go forever and you say, okay, maybe in the next million steps I might get it, but you didn't get it. Then you say in the next 10 billion steps I'll get it. You never get it. And so you cannot tell. So recursively enumerable languages are very complicated. And then there are things that are even more complicated that we didn't even mention. And those are kind of basically, you could call it impossible. But, they are called complicated languages. Non-R, we call them, non-recursively enumerable. So that is to kind of show you the ending. Now, before we get to the ending, we have 2:47, we have to go to 3:15, we have about 30 minutes, we can do this. But if we can't, I wouldn't rush it. So I will spend the time kind of making sure I finish this correctly. So let R be subset of N be an n-ary relation on N. We define the characteristic function by chi sub R is 1 and 0. So you must have seen in discrete math, if the thing is true, you put 1, right? So I'm going back to again what the textbook says. The textbook says 1 for yes, 0 for no. I said, okay, textbook, you win. So chi sub R of X is 1. So remember, X is X1 to Xn. It's N input. And you say this guy is in the relation and this guy is not in the n-ary relation. And so relation doesn't always mean binary. It could mean n-ary. And here is the X, X1 to Xn. Okay. Now you have another function called the characteristic function is one function. The other function is called the affirmative function. What does that mean? It's like, is the yes function. It says yes, if you're in, but if you're not in, it doesn't say anything, right? It says, I don't know, right? No, it doesn't even say, I don't know. I don't know means, could mean yes or no. It just says nothing. So if you are thinking of it as a program, it will tell you, it will halt and say yes. And if you are saying that it's undefined, it might halt and say no, it might not halt, and so you don't know. So it's only is going to give you an answer if the thing is positive, if it's yes. Right? Just like the thing I explained to you about proof. If there is a theorem and you're generating all the theorems, eventually you can generate all theorems and eventually it will show up in a list. But if it's not a theorem, right? Because what is a theorem? A theorem is like something that has a proof. And if you generate all possible proof, you will get all the theorems. But if something is not a proof, doesn't have a proof, it's not a theorem, then you will never see it in the list. But you won't know that you won't ever see it. Because remember, you can't see all the theorems at once. You only see them one at a time. And eventually, you don't know how long you have to wait. But if something is a theorem, you will eventually see it if you live forever, like God. But if you don't live forever, then, and I think all of us, will die. So forgive me for saying that. But I never knew anybody who lived forever. A human being is. I know fiction that they live forever. Okay, so let's so we have these two functions, and then we say the n-ary relation is recursive relation if its characteristic function is a recursive function, and it is semi-recursive if its affirmative function is a recursive function. So you can see the importance of these two things, this one and this one. This tells us, hey, you don't need to start back from scratch. Do you want to know if something is recursive relation? Just go to the characteristic function and see that it's mu recursive. So you're thinking, oh, everything boils down back to, again, mu recursive function or recursive function, whatever they call it. And you're thinking, oh, okay. So as an example, let R be the one-ary relation defined by chi sub R is 1 if X is odd and 0 if X is not odd. So you're thinking, okay, I think this is the modulo thing. This is testing to see if you're odd. If you're 1, you're odd, yeah. And if you're not odd, I put 0. Okay, that's a relation. And this is the characteristic function. So it's a unary relation because it takes one input, right? If it's binary, it will take 2 inputs. So now, chi sub R is a recursive function because why? Chi sub R is equal to H1. You're thinking, hey, wait, what is that H1 again? Yeah, you are right. H1 is 1 if you are odd and 0 if you're even. Yeah. H1. This guy is H1 and H1 is recursive. So you're thinking, okay, so this guy, R is a recursive relation and you're done. You're thinking, and that was too easy. All right. And R be the binary relation defined by x1, x2 is member of R if x1 is greater than x2. So you're thinking, okay, greater than, that's a binary relation. I understand. But now it gets complicated. You get 1 if you are greater than x1 is greater than x2. And if it's not, that means if x1 is less than or equal to x2, then you have to put 0. So you're thinking, okay, I would like you to show if this guy is a recursive relation. And remember, we are doing it with a program. If you were doing it with a Turing machine, we already did it with a Turing machine to test if something is less than or equal to. So a Turing machine can do its job too. So that is what is called Turing, right? Decidable. But this is called recursive, right? So you're thinking, okay, I am going to say that this guy is sine of x1 minus x2. You're thinking, oh yeah, that is so cool. If the x1 minus x2, right? If the x1 is greater than x2, it will be positive, and the sign of this will be 1. If the x1 is less than or equal to x2, you'll get 0 here, and the sign is 0, and you're good. You're thinking, okay, therefore chi sub R is equal to this. And I have a program for the chi sub R. So everything about R is answered by chi sub R. And then you're thinking, okay, I have a program for it, therefore this guy is recursive. So you're thinking, that looks easy. And now we get to the usual story. What is the usual story? The usual story is that just like when we were talking about regular languages, we said, hey, a regular language, is the union regular? Is concatenation regular? Is intersection regular? Is complement regular? So you're thinking, Professor, but you didn't say anything about concatenation. Well, because we are not dealing with strings. We are dealing with natural numbers. So you're not concatenating natural numbers. But we can talk about intersection and complement and union, right? And A minus B. So I say, okay. So if A and B are n-ary recursive relations, then so are A complement, A intersection B, and A union B. You're thinking, oh, so what does this mean? It means that if A and B are nice, they are recursive, then A complement, A intersection B, and A union B are nice. And I didn't put A minus B, but I could have put A minus B too, right? But, you can't put everything because it gets too long. If you're writing a book, you're going to put A minus B and A symmetric difference B, and then you tell the person, do D and E for homework, right? But I know students don't like me to say do for homework. They are like, no, we have enough homework. Okay, so this is what you call a proof. And that's why I am going to spend a little time on it, because every time a proof is, sort of like hated by the students, and they're thinking, man, I hate these proofs. They are awful. But, when I was going to school, I found that proofs are the easiest thing. Why? Because you know when you're right. With a calculation, you might make a mistake. With a program, you might make an error. But with a proof, you know you're right because it's logical. So let's see what we have to do here. So you're given that A and B are recursive. And as I said, that means mu recursive. So you say, okay, now chi of A complement of X is equal to 1. So let me erase this. I apologize for that. These 3 marks, these things shouldn't be there. Right? Yeah, it's just 1. Okay. 1 if X is member of A complement, and 0 if X is not member of A complement. So it's end up being 0 if X is member of A, and 1 if X is not member of A. Right? So you're thinking, because to be not in this means to be that. And to be not in A complements means that to be in A complements, it means you're not in it. So this came down there. And this came went there. Okay. So chi sub A of C is exactly 1 minus chi of sub A of X. Because you're thinking, yeah, this is 1 minus the 1. And then 1, when you get here 1, you get 1 minus 0. So you get exactly that. And so you say, hence, chi of A sub C is equal to, you got to write this now in programming language. Minus, and this is the 1. Now, you're thinking, Professor, I see. You have n input. That's why you put I1, n, because you want to pick out one input, because Z doesn't operate on anything. Z has to operate on one variable. So you pick out the first input, take the Z, make it into 0, take the successor, make it into the 1. That's your 1 here. Yeah, that's the 1. And this is the second thing. You're thinking, okay. That's it, minus of that. And you said, so A complement is a recursive function. And the question usually comes just like that. And you're thinking, I think I can do that, right? Now, how about the intersection? The intersection is, again, very nice. So you say, okay, what is chi of A intersection B? So remember, if you want to show that A intersection B is a recursive relation, you have to show that this characteristic function is mu recursive. So you're thinking, okay, chi of A intersection B is 1 if you're in AB, A intersection B, and you're 0 if you're not. And then you're thinking, okay, if you're both in A and B, I will take this and I get 1 times 1. And as soon as you're not in one of them, or you're not in both of them, you'll get 0 because one of these two things will be 0 and you'll get 0. You're thinking, okay, I'm done. Well, you're not done. You're nearly done. So you can say chi of A intersection B is mod of chi of A and chi of B. You're thinking, yeah, that's it. So all you did was, you took the program for chi of A, took the program for chi of B. So how do I know these two programs are recursive? Because these guys are, if A and B are recursive relations, then these two guys will be recursive functions. So you're like, so that is recursive, and then the mod makes the whole thing, another recursive function. Because you can If you take two recursive functions and you combine them with mul, you get another recursive function, and it does the job. And so you can say, hence, A intersection B is a recursive relation. So far, so good. And you're thinking, I think I like this, right? Now, chi of A union B is a little more complicated. So you're thinking, why do you say that? Well, I will explain here. What is A union B? A union B that's I don't like that, how ugly it is. So I wish I could have written better. Let me pull this thing out more here. A union B. A union B. That's a nice union. Is equal to A union B complement, and then the complement of all of this. Which is equal to A complement intersection, De Morgan law. You know, our friend De Morgan. I got a wrong guy here. That's square bracket, because I want to match it. Square bracket, complement. And you're thinking, okay, I think I got you there. So now we are ready to do the job. And I just put the answer here quickly. So you're thinking, I want chi of A. The chi of A is bad. Sorry about that. I want chi of A union B. And this is going to be 1 minus chi of, that's complement, A complement intersection B complement. That is not good. Sorry about that. Take him off. Right here. All right, I took him off and everybody came out. Okay, then this is equal to, because that's there. And then you're thinking, but I have a thing for this, it's here. So it's 1 minus chi, okay, of A complement times chi of B complement. Come on, the thing. Maybe, how some days the mouse works good, some days it doesn't work good. And let me just put a little wrong parentheses around this. You're thinking, okay, I see what you're doing there. Put the dot higher. Okay, and then you say, okay, so how in the world did you get this? Okay, so the 1 is the 1. And then this guy, you get the mul, and then this guy is 1 minus A complement. So A complement is 1 minus chi A, and this is 1 minus chi B. And you're thinking, oh, I see. And then you just wrote everything out. Now, when I wrote everything out, I get this is equal to all these complicated things, because I wrote what the 1 was, I wrote what the 1 was, I wrote what the 1 was, I wrote the mul, I wrote the monas, another monas, and another monas. You're thinking, oh my God, you have 3 monas, and you have a multi on top of that, and then you have this I sub 1 comma n to pick out the x1. Okay, but that's it. A union B, you got it. And you see how I got it naturally from the intersection. So you're thinking, okay, but there is another way we could have done it. We could have said A union B is chi A plus chi B minus chi A multiplied by B. And so you're thinking, well, this is nicer. Why didn't you tell us this, Professor? Because then I have a hard time explaining how I got this. But it checks out too. So this is good, and it takes a little longer. And this is good. It takes shorter, but it's harder to explain. So you're thinking, oh, okay. So much for Tsuda. Now, this is the thing about intersections of recursive relations. Now, there is another thing that we call semi-recursive. And what is the difference? In the semi-recursive relation, you have this undefined part. And that's what causes all the craziness. By the way, after this, your misery will stop. That's why I showed you the end of the chapter. I showed you the end of the chapter to show, these are the things that correspond to each other, right? But your misery will stop because we will go to complexity theory, which is, not coming in your second test because that's the new chapter, the last chapter, right? So I am allowed to say that because I am supposed to cover the material thoroughly, and I am able to cover it for this chapter, but that one I wouldn't be able to cover thoroughly. I'll only be able to give you an introduction. So I am coming now to what is called semi-recursive. So if A and B are n-ary semi-recursive relation, then so are the intersection and the union. But the problem is, you cannot say the complement is semi-recursive. So remember, what does semi-recursive mean? It means it's kind of the yes part is good and the bad part you don't know. So if you take the complement, then you don't know anything because the good part you don't care, but the bad part you don't know. So you can't say anything about the complement. And so you're thinking, man, so it's like the halting problem. Let me go back to that because this is a thing that if you are going to leave this course, everybody's going to say, so did you talk about the halting problem? Did you talk about recursively enumerable? And they're basically the same concept. So what is the halting problem? It's like, if you give me something, can you tell if I will halt? Yes. But can you say yes or no? No, I can't say yes or no. If you will halt, I will halt and tell you yes, you halted. But because I just simulate what you are going to do. But if you don't halt, I can't tell. Because I can only do what you're doing. I can simulate you. And then if you halt, I will halt. So I can know yes, but I can't know no. And then if you take the complement of the halting problem, and you say, can you tell me if I can't halt? Then no, there is no machine to do that. So there is the machine to tell you when you will halt. Or if you will halt, only the positive part. But if you don't halt, the machine won't tell you. Because it will not stop, right? And so it can't tell you. So this is the problem with semi-recursive. It's a misunderstood concept. Suppose these guys are semi-recursive relations. Then these guys, the affirmative function will be semi-recursive. And let me repeat what the affirmative functions are. It's what we wrote here. It's 1 if you're in and undefined if you're out. So it's different from being 0. 0 means I give you something, but when you say undefined, it's like, I can't tell you what it is. You give me it as input, I won't stop. I won't produce an output. But if I can produce 0, it's out. So undefined means, I am computing and forever going around in circles. So you can't know. Okay. So now, it turns out that it can be shown that a function is recursive if and only if the f is equal to mu g comma 0. So you're thinking, what? F is recursive if and only this? Yes. So what does that mean? It means you are a mu recursive function if you have to only do one mu recursion. And you're thinking, oi, why didn't you tell us that before? Well, that's hard. But most of the time we did it. But it's not easy to show you. That's why I didn't show you. But it says that, if you are a recursive function, then you only need one of these minimization operations. And the rest you will do with primitive recursion. So this is the key of the thing. So how do I get a program for this? I get a program for alpha of A intersection B is 1. This is the definition here. So it's 1 if you're in A intersection B, and it's undefined, you're not. So what you do, you say you look for the smallest value of y, such as g of A of xy plus g of B of x comma y is equal to 0. So if you're 1, and you're in both of them, that means this program will hold and produce a 1. This program will hold and produce a 1. And then you look for the smallest y such that is so. And you're thinking, oh, okay. So the alpha of intersection B is mu of this, and then you're good, right? And then the same thing for union. The union, you say, I want 1 if you're in one of them, and I want, undefined if you're in, not in either of them. So you say, okay, I am going to not put plus, I'm going to put multiply, because as soon as one of these gets 0, it doesn't matter what this guy is, you will get 0. So 0 times something, as soon as one of them is 0. So if you're in A, this will be in 0 for some, value of y. And if you're in B, this will be, so whichever, as soon as you reach that y, the whole thing collapses to 0. And you're thinking, okay, the product is 0, therefore, say that you are in A union B. And so, again, we get this thing here, and you say it works. And so that's why this is. Now, I'll put note, if A is semi-recursive, n-ary relation, it does not always follow that this is a semi-recursive relation, right? For example, let R be the binary relation and N defined by, same thing, Turing machine halts, right? Then R is semi-recursive relation, which is not recursive. And this forces R to be a non-recursive, non-semi-recursive relation. And you're thinking, all right, if A is semi-recursive, A complement is not even semi-recursive, it is bad. So you're thinking, couldn't A complement be half good? And there is a final theorem that tells us. The final theorem says, if A and A complement are both semi-recursive, n-ary relations, then A must be a recursive relation. So that means that if you can say yes for the A with one program, and if you can say no for the A with another program, then I can combine those two programs and alternate them, and sooner or later I will get a yes or no answer. That's the whole idea. So this is the proof of it, and then we'll stop after that. Suppose A and A complement are semi-recursive relations. Then chi sub A and chi of A complement will both be recursive partial functions. So as in the proof of proposition 4, we can find recursive total functions so that chi sub A is equal to mu g comma 0, chi sub A complement is mu of h comma 0. And then I want to make something for chi sub A. So I want to get a 1 and a 0. I don't want to get 1 and undefined. So what do? I make it to be smallest y so that this is equal to 0 if x is member of A, and smallest y so that this is 0 if x is member of A complement. And you're thinking, oh, okay. And when you do that, you will get, if you're in, you look at the G, you will get this. Smallest y is at g of x comma 0, smallest y is at h of y plus 1 is equal to 0. So remember, this is saying the smallest y minus the y. So if you put this into here, it's the smallest y such that h of x y plus 1 is 0, because that takes care of this minus 1. And then you say, this is, you want the two of them, the minimum must be 0, right? So you're thinking, wait, I don't understand. The smallest y such that the minimum of these two is 0. What do you mean by that? Well, this is again just like how I was telling you, you're running the program simultaneously. When you run a program simultaneously, you're saying, okay, I am not going to run it one after the other because this first program will not halt if you're out. Second program will not halt if you're yes. But if I run them one after one step of each, sooner or later, one of them has got to say yes or no. And that's why I will always halt. And then whoever said yes or no, I say that's the answer. So in terms of programming with a Turing machine, it's easy. In terms of this thing, it's complicated because you got to I don't understand this chi sub A. But just to make you relax, this part I am not usually bringing. If you look at the exam, I am not usually bringing this until the final exam. I bring recursive relation in the final exam, and I go up to, recursive functions, and recursive relations comes in the final exam to make life easier so you can catch up. And so this tells you that this theorem, proposition 5, is true because this function min of this is just x minus this. You're thinking, I didn't know that. Well, this is in your homework problem. That's why I didn't do it earlier. We can find max and we can find min. But you're thinking, suppose I want the minimum of 3 and 4, 7. Okay, minimum of, let's say, 5 of 7, because 5 is closer. So you're thinking, okay, according to me, it's you take 5, minus 5 minus 7. And you're thinking, 5 minus, that's 0, so it's 5. You're thinking, okay, smart guy, what is minimum of 5 and 7? Minimum of 7 and 5. You're thinking, okay, I am giving you this example to show you it makes sense. This is equal to 7, according to our definition here, minus, right? 7 minus 5. You're thinking, yeah, that means that's the x and that's the y. I agree with you there. And let me see you produce the minimum, right? There's a dot here, you know that. A dot and a dot here. Okay, and then you're like, oh my God, this is 7 minus 2. And it's 5, and you get 5 again. So you said, I think it will work for everything. Yes, it works for everything. So because of this, you can say chi sub A is this, and then you write this is writing the program, and then you're saying, okay, you're good. This chi sub A is a recursive total function, hence A is a recursive NRE relation. You're thinking, my God, this is cool, but it's complicated. So we'll wait for it in the final exam. The last question or the last definition is that a language L is recursively enumerable if when you code L, it's empty set, or it can be coded as the range of a total function. So it's like you get g of 1, 0, g of 1, g of 2, etc., and you coded it like that. And then it can be shown that C of L is recursively enumerable if and only if C of L is recursively semi-recursive. And so you get this thing that I told you about before. My time is up, but I don't want you to panic. That is why I have the last chapter in which I have to do, but I want you to say up to, and I will repeat this on the day before the exam, up to Turing